Hello, and welcome back to the course on Physics for Engineers. So we are still on chapter 10 of this course. So before we proceed to the third lesson for this chapter, let us first review some concepts. So in the previous lesson, we discussed about calorimetry involving temperature changes and phase changes. So if you have a phase temperature change, the quantity of heat needed is proportional to the mass, the specific heat, and the change in temperature. If you have a phase change, the quantity of heat needed is just proportional to the mass and a constant called the latent heat. And we also have discussed in the last example of the previous lesson regarding isolated systems wherein heat is a concern. So for this lesson, we will be discussing about the first law of thermodynamics. So before we proceed with the first law of thermodynamics, there's actually a much more fundamental law, more fundamental than the first and second law of thermodynamics. So this law was actually developed later after the development of the first law and the second law of thermodynamics. And since it's developed late, they can no longer change the ordering, the first and the second. So, and since this is more fundamental than the first, then what is more, what's earlier than the first is zero. So you have the zeroth law of thermodynamics. So the zeroth law of thermodynamics is all about thermal equilibrium. So in this system, you have system A, system B, and they are separated by a heat insulator. And you have system C, and system C are actually separated by a heat conductor. So C conducts heat or exchanges heat with system A, and C is also exchanges heat with system B, but A and B are thermally isolated from each other. So according to the zeroth law of thermodynamics, so in this case, if A and B, if A is in thermal equilibrium with C and B is in thermal equilibrium with C, then A and B must also be in thermal equilibrium with each other, even though they are not directly in contact. So this is now the zeroth law of generalization, the zeroth law of thermodynamics. Two systems are in thermal equilibrium if and only if they have the same temperature. So as you can see, this is a very basic law. So this is the law, the most fundamental law in thermodynamics. So for example, if you're measuring your temperature using a thermometer, you are actually the purpose of the thermometer is actually just mimicking your body temperature. So your temperature, your body temperature, and the temperature of the thermometer are actually in thermal equilibrium with each other. But it takes a lot of it's not instant. So it takes time before the two bodies can achieve thermal equilibrium. So thermodynamics is basically involved in heat and the motion of heat. So a thermodynamic system is any collection of objects that is convenient to regard as a unit and that may have potential or tendency to exchange energy or heat with its surroundings. So your body is a thermodynamic system, a train is a thermodynamic system, a boiling pot of water is a thermodynamic system. So those are thermodynamic systems. A thermodynamic process is a process where there are changes in the state of the thermodynamic system. So when we say state, it can mean the pressure, the volume, the number of moles, the temperature of the thermodynamic system. So there is one familiar law or equation which relates the pressure, volume, and number of moles and temperature. It's the ideal gas. So you have discussed this in your high school, you have discussed this in your chemistry subjects. So the temperature here is in Kelvin. So P is pressure, V is volume, N is number of moles, R is the gas constant, 8.315 joules per mole Kelvin, T is temperature in Kelvin. So the first law of thermodynamics is concerned with the internal energy of a thermodynamic system. So this is just the sum of all the kinetic energy of all the constituent particles of the system plus the sum of all the potential energies of the interaction among these particles. And it only depends on the thermodynamic state, not on the path or the process, meaning it only depends on the initial and the final thermodynamic states. So it's just like gravitational potential energy. It doesn't matter how you climb up a building. What matters is the change in height. So the change in internal energy of a system is just equal to the heat absorbed or released by the system minus the work done on the system or the work done by the system. So basically, this is a generalized principle of conservation of energy. And again, it doesn't depend on the path, but only on the initial and final states of the system. And it depends actually on temperature. So basically, the change in internal energy depends on the change in temperature. So N, the number of moles, CV is the molar heat capacity at constant volume. Before we have introduced CP, that's molar heat capacity at constant pressure. So, in order for the internal energy of the system to increase, the heat absorbed by the system must be greater than the work done by the system. So in this case, the system absorbs 150 joules of heat and it only do 100 joules of work. So therefore, the change in internal energy of the system is 50 joules. So this analogy is actually applicable with the human body. Our body is an example of a thermodynamic system. So we eat, we absorb heat through food. So when we eat food, that's actually heat being transferred to our body. So if you eat 150 joules worth of food and you only do 100 joules of work, then the internal energy of your body will increase by 50 joules, and that energy is actually stored as fat in your body. You will gain weight in that case. If more heat flows out of the system than the work is done on the system, then the internal energy of the system will decrease. So this is an example of a decrease in change in internal energy. And in the event that the amount of heat absorbed or released by the system is equal to the amount of work done or by the system, then the change in internal energy is zero. So there are two cases for this to happen. One case is the cyclic process, when the system returns to its original state. And in that case, heat and work is the same. And if you have an isolated system, meaning there's no heat flowing in or out of the system and there's no work done on or by the system, then both of the heat and the work is zero. So still, the change in internal energy of the system is also zero. Okay. So if you have a volume change in thermodynamics, the work done by a volume change at constant pressure is just equal to the pressure times the change in volume. So these are the different signs for heat and work in thermodynamics. So if you have positive heat, again, it means heat is absorbed or heat is entering the system. If you have negative heat, then heat is released or heat is leaving the system. If you have positive work, means the work is done by the system and it's on the surroundings. And if you have negative work, then work is done on the system by the surroundings. So these are the different values for molar heat capacities of gases at low pressure. So let's just consider the molar heat capacity at constant volume and at constant pressure. So you will notice that for monatomic gas, such as helium and argon, they basically just have the same molar heat capacities, because these types of gases can be treated as an ideal gas. So similarly, for nitrogen, oxygen, and carbon monoxide, they essentially have the same CV, and CP. It's 29.1, round off to 29.1, round off to 20.8. So hence, this can be treated as ideal gases. So let's now go to thermodynamic processes. There are actually 4 thermodynamic processes that we will be talking about. So the first one is adiabatic process. So in this process, there is no heat transfer into or out of the system. So Q is equal to 0. So in this case, the change in internal energy of the system is equal to the negative work done on or by the system. The second process is an isochoric process. It's a constant volume process. So if it's a constant volume, there's no change in volume. Therefore, there is no work done on or by the system. So in this case, the change in internal energy is just equal to the heat absorbed or released by the system. The third process is the isobaric process. This is a constant pressure process. So the first law of thermodynamics still holds. So Q minus work. So again, Q is mc delta T, or it can be ml, mass times latent heat, and work done is P times change in volume. So the last process is the isothermal process. So iso means constant or equal. So isothermal means constant temperature. So since the change in internal energy of the system depends on temperature, if there is no change in temperature, then therefore there is no change in internal energy. And in that case, heat is just equal to work. So this is an example of a PVT diagram, pressure, volume, temperature diagram. The y-axis is pressure, the x-axis is volume, and these light blue lines that you see here are isotherms, curves with the same temperature. So the temperature at all points in this light blue curve here are all the same. So it's an isotherm, a constant temperature curve. Okay. Adiabatic, isobaric, and isothermal processes can undergo expansion or compression because there's volume changes in this example. Only the isochoric process has constant volume, so meaning it doesn't expand nor it doesn't compress. Okay. The process A21 is an adiabatic process. So in an adiabatic process, the pressure changes, the volume changes, and the temperature changes. So A is on another isotherm, 0.1 is on another isotherm. So pressure, volume, and temperature changes for an adiabatic process. A22 is a constant volume process. So it's an isochoric process. So in this process, constant volume, but the pressure and the temperature changes. So by the way, A21 is an adiabatic expansion. A22 is an isochoric process, so there's no expansion nor compression here because it's constant volume. A23 is isobaric, constant pressure. So it's actually an isobaric expansion because the volume expands, the volume increases. So the pressure is constant, but the volume changes and the temperature also changes. It jumps from one isotherm to another isotherm. And lastly, A24 is an isothermal process. So A24 is just on one, it doesn't change temperature. So A24 is just on one single isotherm. So constant temperature, but the pressure changes and the volume changes. So this is actually an isothermal expansion because the volume expands. Okay, let's have some examples. Okay, this is a follow-up of that will be later. So this example is called working off your dessert. So you propose to eat a 180 food calorie hot fudge sundae with whipped cream and then run up several flights of stairs to work off the energy you have to take in. So meaning all of the food that you need to eat, you should burn it also, so that the change in internal energy of your body will become zero. So the heat and the work that you do must be equal in this case. So how high do you have to climb? Assume that your mass is 60 kilograms. So by the way, food calorie is different from heat calorie. One food calorie is actually 1,000 heat calories. So the calorie that we have defined before, the 1 calorie is equal to 4.186 joules. That's actually a heat calorie. And when you talk about food calorie, one food calorie is actually 1,000 of those calories, 1,000 heat calories. Okay. So in this case, your change in internal energy must be equal to zero, which means the heat that you absorb, which is 180 food calorie times 1,000, so that's 180 kilocalories, must be equal to the work that you must do in order to burn all of that calories. So the work that you must do is by climbing height, by climbing several flights of steps. So the work done by gravity here is just the change in potential energy. In this case, the work that you do is just the negative work done by gravity. In that case, it's just mgy or mgh. So y is the height of the stairs that you have to climb. So actually, it doesn't matter if the stairs are zigzagging. What matters, the work done is just mgy, the change, mg times the change in height. So we'll assume that you start at zero height. Okay. So we solve for y essentially. So y is just equal to q over mg. So Q is 180 food calorie. In terms of heat calories, that's 180,000 calories. You convert that into joules. So 1 calorie is 4.186 joules. So that's your Q. Your mass is 60 kilograms. G is 9.8 meters per second squared. So 60 kilograms. I'm just going to put the unit here. Times 9.8 meter per second squared, and you will get a value of 1,281 meters. So 1,281 meters. That's actually, if you assume that one story or one floor is 4.3 meters. That's actually approximately 300 stories or 300 floors. So that's actually a very tall building, 300 story building. Do we have a 300 story building here? I don't know. But there's a comment here. Not all food that we eat can actually be converted into work. There's no 100% efficient machine. So most of the food that we eat, we actually excrete it. We actually release that. Because we release that through pooping or peeing. So that one. So the actual height is actually very much less if we take into account the efficiency of the human body in converting food into heat. So actually we will follow through with this example in the next lesson on the second law of thermodynamics. So example number 2. The thermodynamics of boiling water. So 1 gram of water, since the density of water is 1 grams per centimeter cube, therefore 1 gram of water has a volume of 1 centimeter cube or 1 cc or 1 ml, 1 milliliters. So 1 centimeter cube of water becomes 1,671 centimeter cube of steam when boiled at a constant pressure of 1 atm. Compute the work done by the water when it vaporizes and its increase in internal energy. Okay. So the work done for a volume change, so there's a volume change here, is just the pressure times change in volume. So final volume minus initial volume, so B minus B naught. Okay. The pressure here is 1 atm. 1 atm, that's actually 1.013 times 10 to the 5 Pascal. Take note, the standard unit of pressure is Pascal. Final volume is 1,671 initial volume is 1 centimeter cube. So the unit of this is centimeter cube. You need to convert this into meter cube. So 100 centimeter, that is 1 meter. And you raise that to the power of 3 to get centimeter cube. Okay. So there's raised to the power of 3 here, raised to the power of 3. Okay. And you will get a value of 169.2 joules. So that's for letter A. That is the work done by the water when it changes volume from 1 centimeter cube to 1,671 centimeter cube. So what is the change in internal energy of the water? So the change in internal energy is just Q minus the work. So we already know the work. How about the Q? So in this case is an example of a phase change. And it absorbs heat. So the formula that we will use is positive M times latent heat of vaporization. The mass of water is given 1 gram. 1 gram in kilograms is 0.001 kilograms. The latent heat of vaporization of water is 2,256 times 10 to the 3 joules per kilogram. So meaning the heat is 2,256 joules. So you subtract the 2 Q minus the work, and you will get the change in internal energy of 2,087 joules, or approximately 2 kilojoules. So you have approximately 2 kilojoules, or 2.1 kilojoules. So in this example, we consider an ideal gas. So you have 5 moles of an ideal monatomic gas with an initial temperature of 127 degrees Celsius. So it expands and in the process absorbs 2,100 joules of heat and do 1,200 joules of work. So what is the final temperature of this gas? Okay. So the change in internal energy of the gas is Q minus work according to the first law of thermodynamics, and it actually depends only on the change in temperature of the gas. So N is the number of moles of the gas, CV is the heat capacity at constant volume, and you have the change in temperature. So final temperature minus the initial temperature. So the unknown here is the final temperature. Everything else are given. Q is 2,100 joules, the work is 1,200 joules, N is 5 moles, CV, you can look it up in the table, it's actually 12.47 for ideal monatomic gases. Initial temperature in Kelvin is 127 degrees Celsius, so in Kelvin that will be 400 Kelvin. So 127 degrees Celsius is 400 Kelvin, 400 Kelvins. So you do that and you will get the final temperature is T naught plus Q minus work over N times CV. So you substitute all of the values and you will get a value of 414 Kelvin. And you convert that to degrees Celsius, you will get 141 degrees Celsius. Easy peasy. So in this case, the final temperature of the gas is 141 degrees Celsius. So again, if Kelvin is the required unit, then you answer 414 Kelvin. So for our last example, this is an example regarding comparing the different thermodynamic processes. So a series of thermodynamic processes is shown in the pressure volume diagram, PV diagram. So in the process A to B, so A to B is an isochoric process. And in this process, the system or 150 joules of heat is added to the system. And in the process B to D is a constant pressure. So at the pressure of 8 times 10 to the 4 pascals. In this process, 600 joules of heat is added. So the first question is, find the internal energy change of the system in the process A to B. So in the process A to B, for letter A, we are asked to find the change in internal energy in the process A to B. So basically, this is just the heat absorbed in the A to B process minus the work done or by the system in the process A to B. But A to B again is an isochoric process, constant volume. Therefore, our work is zero. So therefore, the change in internal energy of the system from A to B is just equal to the heat absorbed by the system. So in this case, A to B is 150 joules. Now, for letter B. For letter B, you are asked to find the change, the internal energy change, the process A to B to D. Okay. So the change in internal energy from A to B to D. So in order to get this change, you just actually need to add the change in internal energy from A to B plus the change in internal energy from B to D. So from A to B, then from B to D. So from A to B, we already know this one. It's 150 joules. So all we need to do, or all we need to look for, is the change in internal energy from B to D. So we already know this one. And this one is just heat absorbed from B to D, which is actually given 600 joules minus the work done from B to D. So from B to D, this is isobaric expansion. So the volume actually expands from 2 times 10 to negative 3 meter cubed to 5 times 10 to negative 3 meter cubed. So the work done from B to D, this one, is just the pressure, which is 8 times 10 to the 4 pascals, times the final volume, which is change in volume. In the final volume minus initial volume. So this case, you have 8 times 10 to the 4 pascals times the final volume is 5 times 10 to the negative 3 minus the initial volume is 2 times 10 to the negative 3. Final unit is joules. And you will get a value of 240 joules. So this is the work done from B to D. So you already know this one. Change in internal energy from A to B, it's 150 joules. The heat added in the process B to D, it's 600 joules. And the work done from B to D is 240 joules. So you add all of those and you will get the change in internal energy from A, in the process A to B to D, is equal to 510 joules. Okay. So let's now go to letter C. So in letter C, we are asked to find the total heat added in the process A to C to D. Total heat added in the process A to C to D. So the change in internal energy from A to C to D is actually the total heat added in the process A to C to D minus the work done from A to C to D. Now, since the change in internal energy doesn't depend on the path, meaning no matter what path I take, A, B, D, or A, C, D, the change in internal energy is the same as long as the initial and the final states are the same. So meaning this is also equal to delta U, A, B, D, which we have obtained in letter B. So this is the unknown. We already know this one. How do we get work from A to C to D? So the work from A to C to D is just the work from A to C plus the work from C to D. Now, A to C is an isobaric process. C to D is an isochoric process, constant volume. So meaning from C to D has no work. So all we need to do is to get the work from A to C. So the work from A to C is just the pressure times the change in volume. So V is from A to C. So VC minus VA. So you substitute that one here, solve for QACD. So QACD is basically just delta UABD plus the work done from A to C to D, which is just this one. And substituting all of that, you will get 600 joules. So for letter A, the change in internal energy from A to B is 150 joules. The change in internal energy from ABD is 510 joules. It's also the same change in internal energy from if you take the path ACD. And lastly, the heat absorbed, total heat absorbed in the process ACD is 600 joules. So that is now the end of this lesson. So the first law of thermodynamics is all about the change in internal energy. In the next lesson, we will be talking about the second law of thermodynamics, which will now focus on how heat flows into a system. So we will focus on heat engines and refrigerators. So I will see you again in the next lesson.